So we stopped after the summarizing loop PVP. So now let's look at an improvement or another variant of belief propagation called tree-reweighted BP that basically addresses some of the disadvantages of BP. So the key idea of tree-reweighted BP is to cover the graph. So we have a graph here with several loops. The idea is to cover the graph with a set of trees. Okay, so for example, we could have one tree like this, where this is the root, and another tree where the root is this factor node. And taken together, these two trees are covering all the edges of the original factor graph. So then we are going to count how many times each edge appears in these coverings. So some edges appear in both, and therefore they get an appearance probability of 1, while other edges only appeared in one of the trees, and therefore they get an appearance probability of 0.5. Okay? So to each edge, we are going to associate the appearance probability that we are denoting by C sub IS. Okay? All right. So if you do that, we're going to define another entropy approximation different from the beta entropy, where the entropy is written again as a linear combination of variable entropies and factor entropies, but where the coefficient associated with the variable entropies is 1 minus the sum for all factors S of the counting numbers of the corresponding edge, CIS. Okay? So if all appearance probabilities were 1, this will become the degree of variable I, and this entire thing would revert to the beta entropy approximation. In general, this is different. And if you think about it, the only way in which every appearance probability could be 1 was if there was a single tree covering the entire graph, but in that case, the graph would be a tree. Okay, so this means that the only situation in which this tree-reweighted approximation could be the same as the beta approximation would be for a graph without cycles. So in general, this is a different approximation, and it turns out that this one is actually a convex approximation, unlike the beta entropy. This is always convex, and it's also an upper bound of the negative entropy and of the log of the partition function. So this approximation addresses two of the limitations of BP, which was the existence of local minima caused by the fact that the entropy approximation was not concave, and the fact that you didn't have neither a lower bound or upper bound. So with this, you can actually build upper bounds, which are convex. To use that algorithmically, everything is very similar to the message equations that we had in the standard belief propagation algorithm. The only difference is that we have some extra exponents going on, so exponentiating the messages. So for example, if you take the variable to factor messages, first of all, the message that comes in the opposite direction is actually taking part in this expression. And we also have the edge appearance probability exponentiating every message that comes from a factor to the variable. Okay, so again, if this was 1, this term would cancel with this one, and you will recover the standard messages in loop PBP. All right, so one thing to note is that we still, to compute these messages, the only thing that we need to do is still to compute local marginals, okay? Because this exponentiation of the messages, after doing that, we can reduce these problems to just marginalizing. So we can use the same tools that we used for BP, but now use them by building this tree-reweighted scheme. So here are some advantages and disadvantages. So this is still simple to implement, as we have just seen. Now the entropy approximation is concave, so this algorithm doesn't have local minima. Also, it gives an upper bound on the negative entropy and on the log of the partition function. So we can use this to build upper bounds. There's a lot of knobs here that we can tune. We can try with different coverings of the graph, choosing different coverings, so different choices of trees to cover the original graph. This will give rise to different appearance probabilities. On the other hand, this is also, in a way, a disadvantage because if you need to tune these, we need to find a way of doing that, and there are a lot of free parameters here. On the other hand, I've seen this in practice. Sometimes these upper bounds are usually very loose. Okay, it depends on the problems, of course. As you know, everything in BP, if it works well or not, it's hard to establish things theoretically. Most of it comes, you know, with trying it out and see what happens. So these upper bounds are sometimes very loose. Also, this algorithm is not necessarily convergent. Even though if we do dampening, which is basically, so the meaning of dampening is when you compute a new message, instead of computing the full update, to interpolate the new message with the previous one. So by dampening, in practice, usually these things converge, even though I don't think this is proved theoretically. And again, the final beliefs that we obtain may not be realizable marginals because they may end up in the local polytope and not in the marginal polytope. All right, so still we have this second row of the table. Local operation is still computing marginals. Now let's look at another algorithm, the norm product BP, that subsumes the previous two, okay? So again, this relies on a convex approximation to the entropy using counting numbers, okay? So now instead of coming up with a covering of a set of trees that cover the original graph, we directly specify these parameters Ci and Cs. These are called counting numbers. And then we define the entropy approximation as the combination of these two numbers. So if these two numbers are non-negative, because each of these entropies is concave, then this is going to be also a convex, a concave approximation. And now what we are going to see is that the messages that will come out from this approximation are going to become norms. And this is the reason why this is called norm product BP. So this is just a recapitulation of what a norm is. So this is the definition of a LP norm, basically summing each entry in absolute value of x, raising it to p, and then exponentiating the sum to 1 over p. Okay, so if p is 2, this is just the standard Euclidean norm. If p is 1, this is the L1 norm. If p is infinity, this is going to be the maximum component of x in absolute value. But in general, you can use any value of p greater than 1, greater than or equal to 1. All right, so here are the messages for this algorithm. And this is where the norms come into play. Okay, so when computing the variable to variable, the factor to variable messages, we are computing this expression, raising each element to 1 over Cs, the counting number for the factor, and then exponentiating the sum to Cs. So this is the 1 over Cs norm of this vector, the vector with these components. Okay, so again, we can still compute all these messages if we can compute local marginals. For given a black box that computes local marginals, we can also compute these norms. All right, so here is a very quick summary. Again, we have a concave approximation. This algorithm is always guaranteed to converge. So there is a relation between this procedure and an optimization procedure called primal dual block ascent. This is like a coordinate descent algorithm. But for convergence to hold, we need to use a different schedule of the messages that prevents us from computing these messages in parallel. Okay, so basically, when you update a factor to variable message, we also need to update all the factors that are surrounding that variable, that are basically connected to that variable. So you cannot compute first all variable to factor messages and then all the variable to factor messages. We need to compute things in a particular order. And also the final beliefs may not be realizable marginals. This is basically something which happens with all these message passing algorithms. All right, so with this, we end some product algorithms. Is there any question about this set of algorithms? All right, so in that case, let's proceed to max product. So one thing that is actually quite important is that if you have devised an algorithm for computing marginals, we can turn that algorithm into an algorithm to compute the map. Okay, and the reason that allows us to do this is by defining this function here, z epsilon, where epsilon can be regarded as a temperature parameter. Okay, so what you are doing here is to exponentiate the variable potentials and the factor potentials by 1 over epsilon, and then we exponentiate the entire sum to epsilon. So if epsilon is 1, this is just a partition function. This is a sum over all scores for every possible assignment. When epsilon tends to 0, this becomes the L infinity norm. And the L infinity norm is basically the greatest component in absolute value. So this is going to give us the mode of the distribution. Okay? So if we try a value of epsilon which is very small, this is going to be very close to the actual mode. And finally, note that if we have some device that allows us to compute the partition function, we can use it to compute the epsilon. We just need to hack the potentials. We need to exponentiate the original potentials to 1 over epsilon, and take the result and exponentiate it to epsilon. And by doing that, you obtain z sub epsilon. Okay? So you can use this trick to compute the mode given an algorithm that computes the partition function. You know, this is related with things like annealing that we might have seen before. So the main idea here is that if you choose a small enough epsilon, any sum product message passing algorithm can be used to approximate the map. Okay, so this means that you can use any of the algorithms that I've talked about already as algorithms to approximate the map. Of course, there is a problem that arises in practice. There is a trade-off between precision and numerical stability. Now, for some problems, when you make epsilon very, very small, you may get numerical issues when doing these computations. In particular, if you use some of the logic factors that I have described. So usually you cannot use a very, very small epsilon. But if you use an epsilon which is too large, the final estimate of the mode might be too far away from the true mode. All right, so another possibility to do to estimate the map is to, instead of use this zero limit temperature idea, directly devising an algorithm of the max product kind. Okay, this leads us to max product BP, where the only change is that the factor to variable messages we replace the summation that we had there by a maximization. Okay, so now to compute the message from a factor to variable, instead of summing over all possible configurations here, we're going to take the max. And again, we have this fact that we can compute the messages by looking only at the factor beliefs. Okay, the difference is that now we don't marginalize the factor beliefs. Instead, we compute something which is called the max marginals. So the max marginals are when we fix a particular value of a variable, in this case yi, so we fix the variable, the value of the variable I to yi, we want to compute what is the best configuration that is consistent with this variable and maximizes the overall score. Computing that for all possible values of yi is the set of max marginals. So, so this algorithm, if the graph has no cycles, these beliefs are going to converge to the global max marginals. So the final values that we're going to get in our beliefs, Pi and QS, they're going to correspond to the global max marginals associated with this distribution. Okay? So then, if you look at what is the y high and ys, that leads us, that maximizes the max marginals themselves, this will be associated with the configurations that give the map. Okay? So we can use a very similar algorithm to some product that is going to give us the true map. Again, we have this usual thing that if you have cycles, this is not guaranteed to converge, and in this case, this is even worse because in the sum product case, we knew that we could interpret the sum product belief propagation algorithm as solving a variational problem, but here we are not guaranteed to even solve the linear relaxation of map. Okay, if you want to solve, if you want to devise a message passing algorithms that solve LP map, we need to use other variations of this scheme. Okay, and we're going to talk about those next. All right, so one such variation is the tree-weighted sequential algorithm, TRWS, proposed by Kolmogorov for in the context of vision problems, where the rationale is the same as in the sum product TRBP. So basically, we define a covering of the graph with spanning trees, and then we compute the messages by exponentiating with the edge appearance probabilities. Okay, the equations are the same as before. The only difference is that again we replace the summation by maximization, and you need a particular schedule that is sequential if you want to converge. But so if you do that, we actually are guaranteed to get the solution of the LP map. And again, as the max product loop EBP case, the only operation that you need to perform is to compute local max marginals. So as long as you have a black box that is able to compute local max marginals, and you have that for basically all problems in which you can run dynamic programming, like PCFGs, sequence models, and other problems as well, we can plug them into this scheme and to use TRW, max product loop EBP, or other algorithm that we are going to talk about next. All right, so this fills another line. Now let's talk about another algorithm called MPLP. So this is derived by writing the dual of the LP map problem, the linear relaxation, and then applying a block coordinate descent algorithm to solve this optimization problem. So I'm skipping all the math, but if you do that, if you take the Lagrange multipliers, these multipliers are going to correspond to messages, and the message updates, they need to be computed in a sequential schedule for this coordinate descent algorithm to work. So one advantage of this algorithm is that the progress in the dual objective is monotonic. Okay, so an average update of the messages, you are improving the dual objective. The drawback is that the dual of LP map is a non-smooth optimization problem. And a general fact about coordinate descent with non-smooth objectives is that we may get stuck at a suboptimal point. So for example, you can look at this plot here, taken from one of Bertsekke's book, where the objective that you are optimizing is non-smooth. And if at some point we land up at this corner here, there's no improvement in any direction that allows us to get out of this corner. Okay, so this is a general issue with coordinate descent algorithms. There are some certain tricks that you can apply to get out of this corner, but you know, those are non-trivial. Okay, so the messages in MPLP are quite similar to the ones in the standard belief propagation. The variable to factor messages are exactly the same. The factor to variable ones, they require exponentiating the messages by 1 over the degree of factor s. Okay, so it's the same kind of scheme that we also use in TRWS. Okay, so to summarize MPLP, this is very simple to implement. We just need to compute max marginals once again. So it handles structured and logic factors. We now have this guarantee that this improves the dual monotonically. There are no parameters to tune. The only thing that is involved in the message computation is the degree of the factor. So there's no edge appearance probabilities or anything like that. The disadvantage is that you can get stuck at a suboptimal solution. Sometimes this happens. We are going to see some examples. And we cannot compute messages in parallel. Okay? All right, so next we are going to sum up message passing, and then we'll go to talk. We are going to talk about dual decomposition. So in message passing, we have seen that BP algorithms and their variants, we can use them for both map and marginal decoding. The only operation that we need to perform is to compute max marginals or local marginals in the case of some products. These algorithms are always exact if the graph has no cycles, otherwise they're approximate. We can interpret some product BP as minimizing an energy approximation over the local polytope. There are some convex approximations there are some convex variants of BP that have guarantees in terms of upper bounds. And we have seen two views of map decoding. First, as a near zero temperature limit of marginal decoding, and second, as directly addressing a non-smooth optimization problem. Okay, so before we start dual decomposition, is there any question about message passing? Yes?
So you didn't show us any application, so maybe some practical.
Yeah, we are going to see some applications in section 5. All right, any further questions? Okay, so let's talk about dual decomposition. This is actually a pretty old idea in optimization. It was first proposed in the 60s. In the context of machine learning, it was first proposed by Komodakis. And in NLP, it was done by Sasha Rush and Michael Collins' group as a way of combining two models to build a more powerful model. And since then, it has been quite successful in many problems in syntax, semantics, MT, and others. So the main idea of dual decomposition is the following. We take our original factor graph, and for each edge connecting a variable node to a factor node, actually for each variable node, we are going to introduce local copies of this variable pi. Okay, so we're going to introduce these QIS variables. We can associate these variables with edges that come out of this variable node. And we are going to introduce an equality constraint in our optimization problem. And then we are going to introduce a Lagrange multiplier. We are going to associate that to each of these equality constraints. So let's see this in a more formal way. This is the LP map problem that we had before. So we want to maximize this linear objective subject to the constraint that QS belongs to the probability simplex. We have seen this before. And that PI is a marginalization of QS. Here, this MIS matrix is just short notation for representing these constraints that we have seen before. And what we're doing now is to slightly reformulate this problem by first introducing copy variables, QIS, and also redefining the potentials. So for each variable potential, or log potential in this case, we are going to spread these log potentials to the edges. So we are going to obtain a problem that looks like this afterwards. Okay, so if you take this summation and this summation, we'll get back the original variable potential. So this problem is equivalent to the one that I had before, except that now we have this extra equality constraint. And if we, for a moment, forget that this constraint exists, so if we scratch out this constraint, this problem will be separable in several independent problems, okay? Because this is a summation over factors, and these variables exist only at factor level, okay? So it's this set of equality constraints that is complicating the problem. So what we're going to do is to introduce Lagrange multipliers for these constraints, and we're going to write down the Lagrangian function that you obtain by doing that. So it's basically the same expression that we have in the objective, plus this term here that comes from introducing Lagrange multipliers here, okay? And now you want to maximize this Lagrangian function with respect to P and Q, subject to these constraints, and you want to minimize it with respect to lambda. So if we do the math, we end up with this dual problem, which is minimizing a sum over factors of a function GS that depends on lambda, where lambda, the Lagrange multipliers, are going to be constrained to this linear subspace. Okay? If you are curious about where this constraint comes from, it comes from the fact that if you maximize this with respect to pi, since pi is unconstrained, this is going to explode unless we constrain the lambdas. Okay? So you can take, so actually there's something that I should mention. There is a paper coming out at JMLR that talks about these and other dual decomposition algorithms and gives full details about this. So if you want to revisit these methods, you can take a more careful look there. Okay, so the dual program looks like this, where these functions gs of lambda are regarded as local subproblems. So these functions are local to the factors, and they have this form. So you want to maximize over QS something that involves the factor log potentials, and this sum that involves the potentials on edges plus the Lagrange multipliers. Okay, we can regard this term as penalties that we are introducing to try to make all variables, all copies to agree with the original variables. All right, so then we can minimize these by using a subgradient descent method. So if you do that, and I'm going to skip some of the math, a subgradient of GS with respect to lambda, to compute that, the only thing that we need to do is to solve this maximization problem. So we need to compute for each factor what is the configuration for that factor that maximizes this score. And this score is basically a sum of a score function that depends on the factor plus a term that is a sum over the variables attached to that factor. So if you can compute a local map for a factor, we can also compute this maximum here. All right, so let's see how this looks like taken as the full algorithm. There is a first step where we initialize all the Lagrange multipliers to 0, and then we have this giant loop where at each step, for each factor, we're going to compute the argmax of this problem. This is just a local maximization problem that involves these Lagrange penalties here. And then we take all the solutions for all the factors, and we're going to compute the average of the copy variables, QIS, and we're going to set PI as the average of the copies. So this is like an averaging step, okay? So first we solve independent problems for the factors, then we aggregate everything and compute the average. And finally, we are going to update the Lagrange multipliers by doing a gradient step, basically subtracting, using some step size eta, subtract the difference between the copy variables and the original and the global variables. Okay? And we need to do this until we get a consensus, which means that all the copies agree with the originals, or until we reach a maximum number of iterations. And it turns out that, in general, if the solution of the LP map problem is fractional, if it's not an integer, we'll never get this consensus. Okay, so we really need to specify a maximum number of iterations. All right, so there are some guarantees. We are guaranteed that we are going to converge to an epsilon accurate solution. So a solution that is epsilon close to the true optimum after a number of iterations that scales as 1 over epsilon squared. But the problem is that this is too slow, especially if there are many factors in the factor graph. And this is actually an issue that arises in practice, and they're going to see some plots to see how this can be really, really slow. All right, so this fills another line in this table. This is a projected subgradient dual decomposition algorithm, and the local operation is computing the map. Is there any question about dual decomposition? All right, so let's proceed. So I made a claim that dual decomposition using this strategy can be very slow, and there are two fundamental reasons why it can be slow. The first one is that the dual objective that we are minimizing is non-smooth. And in optimization, the methods that exist for non-smooth optimization are usually have not as good guarantees as the ones when you are optimizing an objective that is smooth. The second reason is that to promote consensus, if you recall how the algorithm works, the only interface between the local problems and the global problem is via these penalty, these Lagrange multipliers that are penalties. So there is no memory at all about the past updates that have been done or about the global state of the variables. So we are going to show other dual decomposition algorithms that accelerate this scheme. The first one was proposed by Jovic and others, and then one algorithm that we proposed ourselves based on augmented Lagrangians. All right, so let's talk first about the accelerated gradient method. The basic idea is to make the dual objective smooth. So this is addressing the first problem with the subgradient algorithm. It's turning the dual objective smooth by adding a perturbation, an entropic perturbation, with a near zero temperature epsilon. So the idea is similar to what I've shown when I talked about this temperature approximation for the partition function. Now, if you do that, it can be shown that local subproblems, instead of being local map problems, became local marginal computations. And there are some methods that can now tackle this perturbed problem, like Nesterov accelerated gradient method, that allows us to improve the bounds, so the iteration bounds, from 1 over epsilon squared to 1 over epsilon. Okay, so we are now 1 order of magnitude faster than the subgradient algorithm. However, there are some practical issues with this. So the first one is that this is usually very sensitive to the temperature parameter. We have the same problem that if you make it too small, we may get numerical instabilities. If you make it too large, the approximation is not very good. Second, it's also quite slow to take off, and we are going to show some plots that show this. So we have this line. The operation here, the local operation here is computing marginals. And now let's talk about AD cubed, which is an algorithm that we have proposed recently. It's also, so that JMLR paper that I talked about is basically devoted to this algorithm. The idea is inspired by the alternating direction method of multipliers, or ADMM. This is also an old method in optimization. It was invented in the 70s. It's a very natural fit to consensus problems. There is actually a monograph by Stefan Boyd and others that discuss ADMM in the context of machine learning problems. So the idea here is to define, to depart from the Lagrangian function to the augmented Lagrangian function. And this is done by introducing this quadratic penalty here. So this first line is the standard Lagrangian, and we now are introducing an extra quadratic penalty that penalizes further the difference between the copy variables and the global variables. Now, with this augmented Lagrangian, there is a standard method called the method of multipliers, where the first step is to maximize these jointly with respect to P and Q, and the second step is a multiplier update, which is essentially the same that we already had in the subgradient algorithm. Now, the problem is that this first step is quite challenging because this term is coupling the Q variables and the P variables. So it's not easy to solve this joint optimization problem. So what ADMM does is to replace the first step by a separate maximization, first with respect to Q and second with respect to P. And by doing that, we get a very modular algorithm, as we're going to see. It's actually very similar to the subgradient algorithm that I've shown before. This is the original subgradient algorithm, as I've shown, and the only thing that we need to do to turn it into AD cubed is to add this quadratic term in these subproblems. Okay? So now we, instead of maximizing a linear function, we need to maximize a quadratic function. Now everything else is the same. So the reason why this is promoting a faster consensus is that now, before the only interface between the global problem and the local problems was these Lagrange multipliers. Now we have access to the current global estimate, PI, and you use that to regularize the local problems towards those that current solution. Okay. So we also have some better stopping conditions. So we don't need to specify a maximum number of iterations. We can actually compute some primal and dual residuals and stop the algorithm after these residuals fall below some threshold. So I'm skipping details here. But just to summarize the theoretical guarantees of this algorithm, so first it's convergent, then the iteration bound is also 1 over epsilon, as the accelerated gradient algorithm. So this is, again, 1 order of magnitude faster than the standard dual decomposition algorithm with subgradients. It also works if the subproblems, the quadratic subproblems, are not solved exactly, but just approximated under some mild conditions. And finally, the lambdas that are estimated in each iteration are always dual feasible. So we can use those estimates to compute upper bounds, and you can use that fact to develop algorithms for exact decoding. And we did that recently in a paper where we applied this for frame semantic parsing. So the disadvantage is that the local subproblems are now quadratic. So this is more involved than in projected subgradient, because there it was just a local map problem. Still, it's very easy and efficient for logic and knapsack factors to solve these quadratic problems. Just to give an idea of what those problems become in the case of art constraint factors. So these are the art constraint factors that we have discussed previously. And the operation that we need to perform is to solve each of these local subproblems is to project onto these polytopes, okay? And we show in these 2 papers that we can compute this projection in linear time with respect to the number of variables that are linked to the factor, okay? So the complexity is not exponential in the variables, but linear. This is the crucial fact that makes it efficient to compute these local subproblems. Okay, so what about structured factors? So in the projected subgradient case, this was a great thing about this method. We could use combinatorial machinery, combinatorial algorithms to compute a local map. Like, for example, if we are combining a sequence model with a PCFG, we can use Viterbi and CKY to compute the corresponding local maps. But for AD-cubed, we now have quadratic problems. So the crucial fact here, and this is the latest thing that we have done in AD-cubed, is that we can use an active set method that solves the quadratic problem as a sequence of local map problems. Okay, so by doing that, this guarantees that to run AD-cubed, the only operation that you need to perform is exactly the same as in the subgradient case, which is basically computing a local map. So this opens the door to use all this combinatorial machinery if you want to compose complex models. All right, so just to give an intuition about how this active set method works, this is the subproblem that arises in AD-cubed, and the issue with that is that the dimension of these QS variables is exponential in the degree of the factor. And the crucial fact that solves this problem is that we can prove that the solution of this problem is sparse. So there is a solution that has only a linear number of non-zeros. So we can represent a solution by using a linear number of configurations for the factor. And the active set method, what it's doing is to seek the support of the solution by iteratively add and remove components. And again, the only requirement is an oracle to solve local map. All right, so I point you to the JMLR paper if you want more details about this. I'm now going to show some plots. So this is comparing here the runtime of AD-cubed with the subgradient dual decomposition algorithm, and also showing how many times you need to call this local map oracle. So there is one important fact, which is both algorithms, subgradient and AD-cubed, we can take advantage of caching. This is something which is actually not possible in several other algorithms, like, for example, the accelerated gradient one. So this means that when you solve a local problem, we can cache the solution that we obtained, and it's often the case that in the next iteration, the problem that you need to solve is unchanged, and you can just use the previous solution that we have already computed. So this avoids calling the oracles for every iteration. So this plot is showing that this line will be the number of times you will need to call the oracles if you didn't use caching. And for both AD-cubed and subgradient, the number of times that we actually need to call the oracle is far below that line. So this is giving huge speedups in practice. And in this plot in the right, I'm showing the time it takes to parse a sentence as a function of the sentence length. And we can see that the subgradient scales worse with the size of the sentence, that ADQ. So this time is in seconds, meaning that we can parse a sentence with 50 words in about 0.05 seconds. So it's not the fastest thing that exists, but it's good enough to be used. All right, so this completes this table. And we are now going to show some plots where we compare some of these methods. So this is an example for a plots grid. So this is a 20 by 20 grid, a pairwise Markov random field, where each variable can take 8 states. So this is a synthetic model. And we are comparing several of the algorithms that we have discussed. So there are some message passing algorithms, these first two. This is the subgradient algorithm, this is the accelerated dual decomposition. And the last two are AD cubed using the active set method, the method that I have described here, and AD cubed by transforming the graph to binarize it, something that we did not discuss. But so the main idea, if you look at let's look at these two, projective subgradient and accelerated dual decomposition. This is the red line, this is the subgradient algorithm, and this is the accelerated dual decomposition. So we can see that accelerated dual decomposition eventually improves the dual, so it converges faster, but it takes a long time to take off. And this is something that we have seen not just for POTS grids, but for many other kinds of models. So even though the asymptotic convergence is better, we often need to wait a lot of time. We need to iterate it many times to start getting interesting values. And so these two, the norm product and MPLP, are two message passing algorithms. And we can see here that MPLP gets stuck in a local optima. Okay, so at some point it doesn't improve the dual. It's probably stuck at a corner, like the slide that I've shown you a while ago. And this green line is AD cubed using the active set method, and this one is with binarization, which is a strategy which is not as good as the active set method. So I didn't discuss here. So is there any question about these plots? This is a synthetic model, a pairwise Markov random fields with 8 states. Okay, so we're going to see some concrete tasks afterwards. For example, this one is for frame semantic parsing. And here we are comparing AD cubed with subgradient dual decomposition method and with MPLP. This is actually an example where dual decomposition, the subgradient method, is much better than MPLP. So this problem involves several logic factors. And one thing that I have observed in practice is that MPLP doesn't do very well if you have logic factors. And this is an example. So actually it's not getting stuck in any of these examples, but it's taking a long time to improve the dual. But if you compare subgradient with AD cubed is usually much faster. So here I'm showing the number of iterations here, but each subproblem takes the same amount of time in both cases. So if this was time, it will be the same.
So this is semantic parsing, semantic parsing?
Yeah, this is independent problems for each predicate. So it's basically trying to get all the arguments and all the roles for those arguments. Yeah, so I didn't discuss that in detail, but this is actually a paper where you do exact map decoding. So we plug AD cubed into a branch and bound algorithm, and we use that to retrieve the exact map. All right, so this is supposed to finish at 5:30, right? I think it is. Okay. So one thing that I want to mention is that this toolkit is publicly available. So if you want to try AD cubed or some of our MPLP or the subgradient dual decomposition algorithm for your favorite factor graph to solve the problem that you are tackling, you can just use this toolkit. So this is implemented in C++, but it includes a Python wrapper. So, you know, thanks to Andy Muller and Vlad, which should be somewhere there, that's worked in this Python wrapper. So this implements these three algorithms for arbitrary factor graphs. There are many factors that are already built in this code, like the logic factors that I've discussed, knapsack factors, some of the structured factors that we have discussed, and we can also implement your own factor. The only function that you need to write is a function to compute the local map. Okay, so this is, you know, the only local operation that needs to be performed by. So actually, okay, this is true if you want to use PSDD and ADCube. If you want to use MPLP, you need to write a function for computing max marginals. And there are some toy examples included, just to give an idea of you know, how simple it is to use the Python wrapper. I have here a notebook in IPython. So okay, for those plots that I've shown for the POTS model, this is how the code looks like. So you need to import the ADCube toolkit. You need to use NumPy, and then you need, in this case, we're defining here the factor graph. So we need to specify what's the size of the grid, what's the number of states, if the potentials are attractive or not, and so on and so forth. Then this is the step where we create a factor graph, and then you populate this factor graph with variable nodes and factor nodes. So, for example, this line of code creates a variable which can have more than 2 states. We set the potentials for this state in this line. And here we have another loop where you create the factors. In this case, all factors are pairwise, but you could use this for other kinds of factors. And then there are some options specific to the different algorithms. In this case, I'm using MPLP, PSDD, and ADCubed. And there is a function where you just solve LP map using any of these methods. So, you know, in this case, okay, so in this case, it will lead to a graph like this. Okay, so this is kind of similar to the plot that I've shown you. I'm also plotting the primal, the current primal feasible solution here. So I don't have a lot of time here, but there are several notebooks for different problems that you can try if you download this toolkit. Okay, so all right, so let's proceed. So summing up dual decomposition, it's a general optimization technique that splits the dual into several subfactors, subproblems, one per factor, and impose that these subproblems must agree on their overlaps. And you can use that procedure to solve LP map, and we have discussed its 3 variants, which are all convergent, unlike some of the message passing algorithms. And they are guaranteed to retrieve the true map if the graph has no cycles. Another advantage of these algorithms is that they can give certificates if the solution of LP map is an integer. So they realize at some point that all variables, all the copies are agreeing with the original, in which case they can immediately stop the algorithm and retrieve the true optimum. Right, and so there are different local operations for different of these algorithms. Okay, so now we are going to see some applications. So we're going to discuss, if there is time, we're going to discuss 3 of them. In each of them, we are not going to spend a lot of time. So before you're doing this, is there any question that you have so far? All right, so let's see some real problems. The first application that we're going to discuss is applying ADCubed to dependency parsing. So this is another toolkit that we have called Turbo Parser. The name Turbo Parser has nothing to do with speed. It actually comes from something used in communication theory called turbo decoders, which is a kind of decoders, you know, in a way similar to the LDPC codes that I showed you in the beginning. And so the idea is to run a parser, define parsing as a problem on a factor graph, and to run inference ignoring defects caused by the cycles. And what we are going to do is to show how we can use ADCubed with the active set methods to build turbo parsers that are fast enough. So this was a recent short paper at ACL last year. This is an important distinction between projective versus non-projective parsing. So in projective dependency parsing, all arcs are constrained to be nested to each other. In non-projective parsing, we allow non-projective trees where you can have arcs crossing other arcs. So the reason why we should care about non-projective trees is that it's particularly suitable for languages that have a flexible word order. And it's also useful even for English, where the word order is quite rigid. Okay, so we are going to devise a model that combines a lot of different scores. So we have scores for dependency arcs. These are the most basic ones. So every pair of words gets a score related with the fact that there is an arc connecting these two words. But we're also going to have some second order scores. Second order scores for consecutive siblings. So this is basically one arc going from a head to modifier and the next modifier on the same direction for that head. Okay? So this is basically modeling horizontal Markovization. We are also going to have second order scores for grandparents, which is basically vertical Markovization. Okay? So this is a score that looks at one arc and the arc that comes out from the child. We are also going to use scores that break these Markovian assumptions. In this case, this is a score for arbitrary siblings. It's correlating the subject of learned with this preposition in. And we're also going to look at add bigrams. This is basically two consecutive words and what are the add words, what are the parents of these two consecutive words. And we're also going to consider some third order scores for grand siblings and for tree siblings. Okay? This has been used by Koo and Collins in the context of projective parsing, but now we are going to use it also for non-projective parsing. All right, so how can we deal with all these parts? So in the projective case, everything is easier because we can do dynamic programming. Okay, so even with the third order scores, as soon as you just use these Markovian dependencies, if you don't use these scores for arbitrary siblings, we can use dynamic programming. But in the case of non-projective parsing, it's much harder because if we move beyond arc-factored models, if you have any score that does not just factor on arcs, then the problem becomes immediately NP-hard. This has been shown by Ryan McDonald and Giorgio Satta. And so we really need to embrace approximations to build an accurate non-projective parser. And there is a lot of work building different kinds of approximations. I'm not going to describe that in detail. The one that I'm going to discuss is our paper from last year, where we applied ADCubed and the active set method on the parts that I have just described. All right, so here's how our factor graph looks like for this problem. So we're going to have variable nodes for dependency arcs. So each variable node in the factor graph is going to stand for a possible pair of words, for a possible arc connecting a pair of words. So these variables are all binary. Either the arc belongs to the final tree or it doesn't. And we are going to have a tree constraint that imposes that the final assignment of arcs is going to define a well-formed tree. Then, to model the consecutive siblings and the grandparents, we are going to introduce head automata. This has been done as well in previous work by Smith and Eisner and Terry Koo and others. Okay, so then for arbitrary siblings, where you don't have this Markovian property, we are going to use easing factors, basically edges connecting two pairs, connecting two variable nodes that model the fact that these two arcs are simultaneously in the dependency tree. And for the third order models, we are going to generalize these automata to the third order. Okay. Finally, for add bigrams, where we had just two consecutive words and we look at what are the adds of those words, that we can tackle with a single sequence model, because it's like a sequence labeling problem. So we're going to compose all these into a single factor graph, and all these problems are local problems that we can solve either with dynamic programming or with by projecting, in the case of the logic factors. And we're going to solve a linear relaxation with AD cubed. And so, doing that, we obtain state-of-the-art accuracies for the largest non-projective sets in the kernel data. And the speeds are very competitive with prior work. Okay, so we are around slightly less than 1,000 tokens per second on each of these languages. And because our model is so, it uses so many scores, we actually get very high accuracies. Right, so one thing I want to mention is that we recently, this year, we extended this approach for broad coverage semantic parsing. This was a shared task at SemEval, and we got the best result by using a very similar model for semantic role labeling. All right, so let's discuss the second application. This was a paper last year at ACL. The problem here is summarization. And let's recall what the problem is. We have as inputs several documents about the same event. In this case, the event is the visit of Obama to Myanmar. And we want to extract the relevant information in all these documents and to generate a brief summary. So something that looks like this. Now, if you think about this problem, there are three things that can make a good summary. The first one is a good summary needs to be concise. Otherwise, it won't be a summary in the first place. The second thing is it should be informative. So it should retain all the important information in the original documents. And the third aspect is that the sentences that compose the summary should be grammatical. So there are these three dimensions, and we are going to formally define each of these three things as a single optimization problem. So, okay, so before doing that, let's look at the most used summarization technique, which is extractive summarization, and where the idea is just to extract entire sentences. So for this particular example, a summary composed of these three sentences could be a good extractive summary. Now the problem is that, for example, there is a very long sentence here that is wasting a lot of time. So if instead of using the entire sentence, we just use a piece of that, maybe we can have a better summary and make room to include more relevant information. So what we're going to do is to jointly extract and compress. So here's what we are going to do. We are going to allow snippets of the sentences by considering as units not the sentences but the words. So in this example, we could use more information coming from different sentences because we are trimming some of the sentences. There's a lot of prior work in these models. Our contribution here is to apply AD-cube to this problem. So compared to extractive summarization, for a given summary size, it's easier to be informative because we now can use information from different sentences, but it's harder to be grammatical because we are in danger that our trimming operations are going to harm grammaticality. So here's why we can define the problem as a global optimization problem. We're going to have indicator variables for every word of every sentence. We're going to denote that as a zn variable for every sentence, for sentence n. Then we are going to constrain the length of the summary not to exceed a budget of b words, which you can represent as this constraint here. And then we are going to define a quality function that rewards global informativeness through a g function, g of z, and that rewards local grammaticality at sentence level. So we're going to have a quality score for each sentence, and they're going to sum over sentences. Okay, so for the grammaticality part, we are going to use a sentence compression model inspired by prior work by Kevin Knight and Daniel Marcoux, where we basically define a factor that is a structured factor where the score decomposes over dependency arcs. So basically, this is an instance of a structured factor. We want to maximize the sum of the arc scores, and we allow only deleting entire subtrees. So if we delete an arc, we are constrained to delete everything which is beneath that arc. So this is an instance of a structured factor, and we can solve this local map problem with dynamic programming, because the underlying graphical model is a tree, and this is just using the Viterbi algorithm for trees. All right, so for informativeness, we are going to use an approach that attempts to maximize coverage. This is inspired by prior work in extractive summarization. So we're going to extract a list of concepts from the original documents, and we're going to define a relevance score for each concept, and we're going to define our informativeness score as a sum of scores for each concept. Okay? So it's probably easier to understand the entire thing by showing the graphical model. This is the part of the graphical model that takes care of the budget. So this is imposing that the length of the summary cannot exceed like 100 words. Then we have structured factors, 1 per sentence. This is taking care of the sentence compression part. And then we are going to extract concepts to the summary. Each concept in our model is just a word bigram. So in this example, Kashmiri separatists is a concept. And to keep track of what are the concepts being extracted, we introduce these variables that are basically computing a conjunction of 2 words, and the output is going to be an event that is either 1 or 0, depending on whether the 2 words were extracted or not. So here, both words, Kashmiri and separatists, are part of the summary. Therefore, this variable is 1. In this example, only separatists was extracted, and therefore, the outcome of this AND gate is 0. Okay? Then, we're going to make a disjunction of this concept token. So this is like a conversion from tokens to types. Okay? We're going to look at our sentences and see in which sentence what are the concept tokens that were extracted, and here we are going to check if there is any instance where we got the concept Kashmiri separatists. So this is basically a OR factor. And then so all these are instances of logic factors, and we're going to use dual decomposition, the AD³ method, to solve LP map. All right, so this problem is NP-hard, and there's a chance that the final solution is fractional. So we need to do this heuristic for rounding in order to guarantee that we obtain a summary, something that can be interpreted as a summary. And so in this paper, we also learned with multitask learning. I'm not going to talk much about this. But basically, the idea is that we use some user-generated data from the Simple English Wikipedia that allows us to learn these sentence compression components. So the good thing about this approach is that you can also learn some of these components of the model separately. And these are the results that we have obtained. So we are comparing here with an extractive system. This is the system that got the best results in the TAC 2008 shared task. These two are 2 systems that also do compressive summarization. This is what we get with the single task AD³. And with this additional training data, we managed to improve the recall, the RUGE2 score, which is the standard metric used to evaluate summarization. We can improve that. And if you look at the runtimes, which is probably the most interesting part in the scope of this tutorial, we are comparing here the runtimes of AD³ with a solver, in this case GLPK. And what you can see is that so AD³ is approximate, and therefore the final RUGE scores are not exactly the same that we get with an exact ILP, but the runtime is much faster. So we can solve an entire summarization problem in less than half a second. So the reason why this is relevant is that these runtimes are not very far away from what you get with extractive systems. So this, is a way of trying to make compressive systems be fast enough to be used in practice. All right. So is there any question? Yes.
So by extractive system, you mean now like systems that extract sentences or that extract on bottom level, like without ignoring.
Oh yeah. So yeah, here extractive systems. I mean a system that extracts the entire sentence. That yeah.
And they will have larger budget anyway. They will consume space.
No. So the budget is the same for all algorithms for all.
All the sentences they are going to use more space.
Yeah, so they basically they end up selecting fewer sentences because they have the same budget and they cannot. But that's an advantage of compressive systems, right? You can include more information.
There is an advantage of this approach, no? With respect to sentences.
Yeah.
You can compress better.
Yeah, exactly. Yes.
I'd like to know how the quality of coding affects to the quality of article or
The quality of what? The grammaticality.
application.
Ah.
You stop by primordial caps, right? And if the lose, then convert after.
So I'm not sure if I understood correctly. Let me rephrase. You're asking if the summaries that you get at the end are grammatical enough to be useful in a practical application? Yeah, so they are not as grammatical as the ones obtained with the extractive system, because in the extractive system it's the entire sentence. So it's usually the best that you can have when it comes to grammaticality. But
My question is the quality of decoding, like quality of validation, how does it affect to the quality of
oh, okay, I see. You're saying that if the relaxation that we are doing is going to harm the final summary that we get? So this is actually one important difference in practice between these two applications that I talked about. For the parsing problems, it's quite common the case that the final solution is integer. For the summarization case, that's not what happens. And my explanation is that in summarization we have several sentences competing, or several words competing to be in the summary, which is like an analogous of like Ising model with repulsive potentials. And when you have these repulsive potentials, the quality of the relaxation is worse than when all potentials are attractive. So in a way, we observed in practice that for summarization problems, most of the solutions are fractional and not integer. But with the heuristic that we used, which is a very simple heuristic, we mapped the final solutions to something that represents a valid summary, and it integrates the quality by a lot. So we compared the solutions that came out from the ILP procedure with the ones that came out from AD cubed. There's a difference in terms of rouge, but if you look at the grammaticality aspect of the sentences, and we have manual evaluation of grammaticality in the paper, we don't see a very significant difference in terms of quality. So I would say that if you devise a smart enough rounding heuristic, you might be safe for at least for this kind of problem. All right, so okay, so finally, let's talk about the last application, a joint model for coreference resolution and quotation attribution. So this is a paper that we presented this year at EACL. So why do you want to do these two things jointly? So you are arguing that these two tasks may benefit from being treated as a joint task. And let's see some examples of that. So the first one is, so you have a sentence here with a quotation, and it happens that the author of the quotation doesn't usually refer to himself as he. Okay, so in this example, the quotation is this sentence, and the author of the quotation is Arthur Watson, and it's very unlikely that this E is coreferent with Arthur Watson, because he will never say a sentence referring to himself as E. Okay. All right. So in this case, this will be the correct set of coreferences. So we have two entities here: Arthur Watson and Pilson E, and 49-year-old Mr. Pilson all refer to another entity. So another aspect is that two consecutive quotes, in this case this one and this one, it's quite often the case that come from coreference speakers. So in particular in this case we have Dorothy Sayers, which is the author of the first quote, and before the second quote there is this sentence, she had it something. Okay, so it's very likely that she refers to the same author as the first quotation. So this is an example where getting the authors of this quotation right can help coreference. And in this case, this will be the correct clustering in terms of entities. All right, so previous work in coreference resolution developed models that where they're trying to get what is the best antecedent for each mention. So each mention can be either anaphoric or not anaphoric. If it's not anaphoric, we can imagine that we are attaching that mention to a root node. So we have a special root node here. If it's anaphoric, then there is an antecedent, and we can represent that by drawing an edge, an arc connecting the antecedent to the current mention. Okay. So in this example, this is a tree, a coreference tree for the previous example, where she refers to Dorothy Sayers, and all the other mentions are non-anaphoric. So if we build a sentence like, if you build a tree like this, we could recover the entities corresponding to these mentions by looking at what are the subtrees that come out from the root. So in this case, we get an entity for Dorothy Sayers, and we get different entities for these other four mentions. Okay? All right, so what we do in this work is to use the same idea for mixing, for building quotation coreference trees. Okay? The idea is extremely simple. We include mention nodes and also quotation nodes. And we constrain the quotation nodes to be leaves in the tree. Okay? Now, if you then look at the subtrees that come out from the roots, we can at the same time get the entities and get the entities that are authors of a quotation. So instead of just defining the author of a quotation to be a particular mention, we get the entire entity that is the author of the quotation. Okay, so let's see an example for the same sentence. We now have these two quotation nodes, the two quotations that are present in the sentence, and the entire entity, Dorothy Sayers, is the author of both of these quotations. Is this intuition clear? Okay. All right, so so the simplest models for coreference, for example, there is a recent paper by Greg Darrett and Dan Klein that defines a model like this, are arc-factored, meaning that we only have scores for a mention and its antecedents. If you want to do something more complicated than that, it's easy to fall into a problem which is very hard. And so the advantage of these arc-factored models is that we can do exact decoding in a greedy manner. So for this model of Darrett and Klein, we can greedily pick what is the best antecedent for each mention, which dynamically builds a tree like this. Okay? However, if you do that in our approach, including these quotation nodes, this will be equivalent to do coreference resolution and quotation attribution independently. And why is that? So if you look at the tree that we have, this will be equivalent to picking the best antecedent for each mention, and then for each quotation, getting the best mention for this quotation. But if you do that this way, we are not correlating the two tasks. We are solving these problems as if they were independent. So if you want to actually build a joint model, you need to do something more involved. And what we're going to do is to add extra scores for two events that are particularly relevant for these two tasks. One is the event that the speaker is mentioned inside a quotation, and the second one is consecutive quotes having the same speakers. So if you do that, to do that, we need to know if pairs of nodes are in the same subtree, which complicates things a little bit, okay? So to do that, we're going to write down a logic program. We're going to have arc variables that denote that two nodes in the tree, there is a relation like parent to child. And we constrain that each variable j, each node j, needs to have a unique parent, okay? Unless it's the root. We're also going to have some path variables that we are going to denote by pi of I to k that tells us that k is a descendant of I in the tree, okay? And we can compose these paths by saying that we can build a larger path by composing a smaller path with an arc that goes from I to j. Okay, so in other words, there is a path from going from I to k if there is a path going from j to k and an arc going from I to j for if there is one such j. So we can represent that as a OR constraint, okay, with the AND constraint here. So we can use our logic factors to model these. And we're also going to have some pair variables, these variables p, k, l, that denote the event that nodes k and l are in the same subtree. Okay, this is useful to say that k and l refer to mentions that are coreferent because they could be two mentions of the same author of a quotation. And to do that, we can reuse our path variables. So k and l are in the same subtree if there is some node I, which is not the root, such that this I is a common parent, a common ancestor of node k and node l. Okay? All right, so so the idea is that we build this logic program. Each of these things corresponds to a logic factor, and therefore we can run dual decomposition, as we've told before, to solve this problem. So we experimented with some data sets. We used the Wall Street Journal portion of the ontonodes with the same splits as in the Connell 2011 shared task. This was for the coreference annotations. And for the quotation annotations, we used the data set created by Silvia Paretti and Tim O'Keefe that is basically also, it annotates the quotations in a subset of the Wall Street Journal. So we can combine these two notations and have a single data set for tackling the two tasks together. To evaluate coreference, we use the standard evaluation matrix. And to evaluate quotation evaluation, to evaluate quotation attribution, we're going to use metrics that are particularly tailored for entity-based quotation attribution. Meaning that we're not just looking if you are getting the mention right, because that mention can be quite uninformative. For example, if you have a sentence saying something like, she added blah, 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 then if you say that the author of that quotation is she, that's kind of useless, because if you don't know what does she refers to. So we have a score that looks at the clusters of predicted mentions and gold mentions describing the correct author. And another metric that we have is one which defines a representative mention to represent the speaker, something which is non-pronominal. All right, so these are the results that we obtain. Okay, so we are comparing here the results on the two tasks, in-coreference and quotation attribution, by using a joint system. We can see that there are some slight improvements on coreference compared with the system where quotation and coreference are made independently. We are also showing here the results obtained by the recent system of Durant and Klein. It's not a large improvement, but it's a significant one. And for quotation attribution, we are comparing also with doing quotation after coreference and quotation and coreference independently, and we also benefit using these two metrics, we also benefit from doing the two things together. All right, so this is all that I have to say about applications. Is there any question? Yes?
Yeah, so did you try just for the coreference resolution task to add second order, third order features? Because your approach allows this.
Yeah, that's a great question.
Whereas in coreference, nobody has done before.
Yeah, that's true. That's a great question. The only second order, it's not really second order, but the only higher order features that we used was the ones that involved quotations. So basically, these two cases, if a speaker is being mentioned inside a quotation, or if you have consecutive quotes with the same speakers. We did not use second order arcs in the tree. That makes a lot of sense. We do something similar for parsing. The challenge here is that these coreference trees are for the entire document. So usually you have a lot of nodes. There's a lot of mentions there. And so things don't scale as nicely as in parsing. But I think it's something that could be something to look at in the future. All right, so, okay, any further questions about this task? All right, so let's conclude. This has been a very long tutorial. So, so we have seen that many structured problems in NLP are NP-hard or very expensive. Problems that involved global constraints, problems where you want to promote diversity, where you want to combine two or more structured models. So the kind of decoders that we talked about here are particularly suitable for problems of these kinds. So we have seen that many of these problems, we can approximately decode them by relaxing an integer program. Also, we have seen that the structure inherent to these problems can be represented with a factor graph. And we discussed two different kinds of algorithms to solve these problems, message passing algorithms and dual decomposition algorithms. Both of them can exploit the structure of the graph, and both of them require some local operations to be performed at the factor scope. So the main underlying idea here is to approximate global decoding by invoking only local decoders. As long as you have a device that you can use locally at factor level, we can compose, you can use this device several times iteratively to approximate global decoding. And the kind of local operation depends on the algorithm. We can have local maps, local map computation, marginal computation, max marginals, quadratic problems. We have seen, in particular, talking now about dual decomposition, that ADCube is a faster approach than subgradient algorithm, both in theory and in practice, while it requires the same local decoders. So I encourage you to use the toolkit that I've talked about if you want to try it out in a new problem. And we also showed some state-of-the-art results in several applications. And that's basically it. So we talked about Turbo Parser. Turbo Parser is also publicly available. The toolkit is also available, so we can just download and try it out. There's a few acknowledgements, and that's it. So that is all that I have. So I'll be happy to take any questions. Yes?
Yeah, so I'm wondering how does this interact, especially the approximation part with learning? From many learning algorithms like perception require that you pick the optimal solution, but then you cannot guarantee that. So given that you actually build several combo models that provide results, so what can you say about that, or what's your experience?
Yeah, that's a very good question. I didn't talk about learning at all in this tutorial, but one thing that based on my experience in some of these problems is that so for parsing, for example, and for nearly all problems that I've talked about, during training we used the LP relaxation as it is. We didn't try to do the rounding part. Okay, and there's actually some things that you can prove. For example, if you learn with the structured SVM, if you consider these outer bounds defined by the local polytope, intuitively, this means that you are not separating with a large margin the true example from the false ones, but also from the wrong ones, but also from a bunch of artificial ones that come from the fractional vertices. So this can give a robust strategy to train a decoder, by using this linear relaxation. I've seen experimentally that this is usually better than trying to do the rounding. Okay, so talking about perceptron, we could have two strategies here. One is to do all the perceptron updates as usual, trying to round the solution that we have. Another alternative is to do that, but use DLP relaxation. And we can, compute the same updates even though the outputs are fractional. And usually the behavior is best in this second strategy. There's a paper that studies that, compares belief propagation with linear relaxations for synthetic models by Kuleza and Pereira. I'm not sure if it's in the references. Oh, okay, so it's not in the references. But if you look at the JMLR paper, there are some theoretical studies that compare the two. Any further questions? No?
So what about the decomposition to compute marginals?
How do we use? Oh, okay. So yeah, I also didn't talk about that. I've seen a paper that does something like that. We can, if you look at the objective functions that we have talked about when we were talking about message passing, this free energy approximation, which is basically a combination of variable entropies and factor entropies. If you use decompositions of the same form, and you consider those things as your local subproblems, the local subproblems that you will need to solve will be marginal computations. So in those formulations, we can also use dual decomposition to get marginals for approximate marginal inference. My experience with marginal inference is that it's much harder than math inference, because with marginal inference there are these two approximations being carried out, and the free energy approximation can be really tricky sometimes, and sometimes things just don't work. So some of the algorithms that I described here, like tree-weighted BP, I've played a little bit with that using the logic factors for parsing, and they work terribly. You cannot generalize these things, so maybe there are problems for which they work very well, but it's hard to take conclusions based on that. So I would recommend that if you can, just try map decoding first. Just don't try to do marginal decoding unless you really need to. All right. Okay, so thank you.